Today we want to look at an example where we're calculating slope of a tangent line and we're going to approximate it with a secant line. The question came up yesterday, how close is close enough? And the answer is you'll just know. Eventually you'll just know. Because this boundary between the discrete and the continuous isn't a well-defined thing. At a certain point, we've chopped things up so fine, it's all just smooth. Or is it smooth? How close is close enough? That's kind of the question that we're getting at today. How close is close enough? It's a question that kind of comes up all the time when you're learning stuff like that. How will I know when to do A versus when to do B? And the answer is, if you have to ask, you don't know yet. You just have to keep going and doing more until you just know. All right. Let's look at an example. Let's suppose we want to find the slope of the line tangent to the curve y equals natural log of x at the point where x is equal to 3. Since we're now talking about tangent lines, I want to bring up the importance of the tangent line so we don't get distracted by silly things like why do we care so much about this tangent line? The tangent line is our best linear approximation of a function near a point. This is why we care about tangent lines. Tangent line is the best linear approximation of a function at a point. We want to think of a tangent line as the best linear approximation of a function at a point. Lines have two characteristics. They go through a point and they go a particular direction. The tangent line, when we're putting it next to a function, goes through the same point and they're going in the same direction. So the tangent line matches the function in all the things that the tangent line can match. Tangent line has two things: location, direction. It matches the function in those two things. The function has all kinds of more interesting stuff going on. Tangent line don't care. It's only got two things: location, direction. That's the best we can do. The tangent line is the best version of that, the best linear approximation of a function near a point, at a point. Let's take a look at what we're trying to build. Let's see if I put this on the, oops, no, stop this. Let's see if I close out my, there we go, Desmos. So here's a function. Here's the graph of natural log of x. We're interested at the point where y is equal to, where x is equal to 3. That's here. We're interested in what's going on at this point at 3, natural log of 3. And we're going to try to make a tangent line at that point. I'll turn off this. Now, the constant approximation is just a flat line. That's not a very good approximation. That matches the value, that matches the 1 point, the location, but it doesn't match the direction because the constant is flat. I want to make a line. I want to match the direction of the function. So what I have underneath is a line that goes through the point natural log of 3, 3 comma natural log of 3, and has a variable slope. And I'm just going to modify the slope until I get some kind of tangent line. So kind of like up to that's a little bit too flat. That's a little bit too sharp. Looks like it's somewhere around this 0.3 if we zoom in. This 0.32 is pretty good. It looks like it's somewhere in there. It's teetering, see, because it's balancing at that one point. It's not teetering because I'm moving back and forth with my finger. It's just balancing it. I'm just kidding. I'm moving it back and forth with my finger. So it looks like somewhere around here, but it's hard to see just visually. And if I zoom in closer, well, we're making a linear approximation, so the line is getting really close to the function the closer we look. This is what we experience all the time. If you look close enough, everything is flat. Right? We look at the surface of the Earth, we know we're standing on something curvy, but our eyeballs are saying this is flat because we're looking really close. We're looking super close. That's not even super close. Every major tick mark here is 1/100th. But looking super close, they look the same. It's really hard to check if we've got it. We just kind of eyeballed it. So that's what we're trying to do. This natural log of 3 plus m times x minus 3, this is a line with the slope of m that contains the point 3 comma natural log of 3. So that's the point slope equation of the line. So if I write y naught plus m times x minus x naught, this is the equation of a line containing the point x naught, y naught with slope m. So y equals y naught plus m times x minus x naught is the equation of a line containing the point x naught, y naught with slope m. We know the point that we want to go through. It's when x is equal to 3. We know the point that we want to go to. It's when x is equal to 3. So the point that we're interested in is 3 comma natural log of 3. One point something. So there's the point that we're interested in. What we need to find is the slope. Now for slope, we're going to do y2 minus y1 over x2 minus x1. We're going to take x1, y1 to be the point that we care about, and x2, y2 is going to be a point nearby. So whatever the y is, I'm going to subtract the natural log of 3 to find the rise. And then x minus 3 is going to be the run. Now what the y is natural log of x. So what I'm calculating is the natural log of x minus the natural log of 3 divided by x minus 3. So there's the change in the y divided by the change in x. If I try plugging it in 3, I get 0 over 0 and we get nothing. So we're going to plug in stuff that is close to 3 and see where things are headed. So just like we saw yesterday, we can't plug in 3 to calculate the slope. We can't plug in 3 because we'll get 0 over 0. And that could be whatever we want it to be. So we're going to plug in stuff close to 3. So we're going to be plugging in values that are close to 3. So I'm going to try 3.1. 3.1 is close to 3. That's a hugely far apart, considering the power of calculator we have. So we're going to pretend this is like back in the day when we didn't have calculators. And we had to look up the natural log of 3.1 in a book. I don't know if you're familiar with this, but if you wanted the natural log of something, you just have to look it up in the book. 3.1, you might actually just remember. But otherwise, you just like look it up in a book. It's like, oh, here's my table of natural logarithms. Find the 3, go to the 0.1 column, and then there it is. But we're all spoiled today. So when we have at 3.1, we get a slope of 0.3279. So I'm going to make a list of delta x and then the slope that we get. So when the delta x is 0.1, we get a slope of 0.3279. Here's an approximation of the slope. There's what it looks like on the calculator. That looks pretty good. And we've gone like super far away, all the way to 3.1. How do we make our approximation better? Move it closer. What am I going to use next? 0.01. I'm super predictable in that way. I'm not going to mess around. We're just going to go a whole order of magnitude closer. Just like right into just doink, next order of magnitude. And let's see what that looks like on our calculating machine. So I don't want to type it all over again. I'm going to insert a 0 there and then insert a 0 there. So now both are going to be a 0.1, 0.3328. At this point, I would flip back over to Desmos, change it to 0.3328, and you would be looking at pretty much the same picture. Your eyes would not be able to see the difference. I don't know, maybe you think, no, my eyes can see the difference. That's why I have my computer set to 12,000 FPS. 60 just isn't good enough. I can see the difference between 60 FPS and 120 FPS. I mean, if you believe you can, I guess you can. I don't know if that would stand up to an empirical test, but Whatever. Whatever makes you happy. I like to listen to the fans in my computer go as well. And look how hard my computer is working. So this is presumably a better approximation because now instead of 1/10 away, I'm 1/100th away. What am I going to do next? Another order of magnitude, just drop in another zero. So go in, insert another zero. Point 3333. Yes. Yeah. I happen to know where this is heading. I have secret mathematical knowledge. I think some of you do too. Some of you just like, oh, it's a third. It's a third. Before you even start the process, it's a third. Just put a third. I'm like, oh, no. You're like, ah. Because if I just keep it to 4, eventually, I'm not going to be able to tell the difference, like what's going to happen next. Oops. And you're thinking, I'm sure, isn't there a better way to do this? I'm like, oh, yes, absolutely. But it doesn't look like the slope formula. And I want it to look like the slope formula because that's literally all that we're doing. If we change the form to that limit as h goes to 0 stuff, then it doesn't look like the slope formula enough. This totally looks like the slope formula. But if I throw in another 0, looks like we're getting this consistent 2/8. We can see what happens every time I throw in another 0, every time I move an order of magnitude closer, it looks like we get more 3s. This brings up the question that we saw yesterday. How close is close enough? Do we see a pattern? And is that pattern correct? Sometimes it's hard to know if the pattern is going to be correct or not, but it certainly seems like we see a pattern. What does it look like we're headed towards if I make my delta x infinitely close to 0? Looks like if I have an infinitely close to 0, I'm going to add more 3s. I'm going to have an infinite number of 3s. And what's that equal to? 1/3. So it certainly looks like. So now I'm going to speculate. Here's me guessing. And then here is me confirming or testing my guess on the calculating machine. 1, 2, 3, 4. And it looks like that's where we're headed. So every time I throw another 0, I get another 3 before the 2, 7, 8 part starts. Eventually, I'm going to run out of space on my calculating machine. It looks like we're headed towards a third. It looks like as delta x is getting close to 0, this number is getting close to 0.3 repeating, or 1/3. In this case, it looks like 0 divided by 0 is 1/3. That's a terrible way to say it. You're too young to hear things like that. So just disregard that part. You're too early on in your mathematical career to say lazy ass things like 0 divided by 0 is 1/3 in this case. That's super dangerous. Then you'd be like, well, then 1 divided by 0 is infinity. Or is it negative infinity? But you don't have a license for that stuff. You haven't passed Calc 1. If you like go out into the world and be like, oh, 1 divided by 0, math cop's gonna get you. Like if you're like up on like if you're just like talking and stuff like that, but if you like text someone's like, oh hey, 1 divided by 0 is infinity, math cops are watching. knock on the door. Excuse me, could you step out for a minute? Is this you? Let me show you a text. It's 1 divided by 0 is infinity. It's like, can you verify that you passed calculus? Well, I'm in calculus right now. Come with us, please. Don't mess with the math pops. The math pops play hardball. Made a whole show about it. Math pops, math pops. What you gonna do? What you gonna do when you divide by 2? Okay, maybe they didn't actually make my show. I mean, that show. I did not pitch it to like any major networks. TLC called me back. That's how I knew I was wrong. TLC is like, oh, we'll make your show. I'm like, oh man, now I feel terrible. Now I know how wrong I was for suggesting that. Huh. Any questions? All we're doing is stuff from Calc 1, and we're trying to, Calc 1. All we're doing is, obviously we're doing Calc 1 stuff. All we're doing is stuff from our first algebra class. We talked about lines, rise over run. We're just playing the rise over run game. The problem is that our rise and our run are both 0 or super close to 0. We're not actually plugging in 0 because then this is not nothing. This is indeterminate. But as x, the delta x gets close to 0, it looks like the slope is getting close to 1/3. That's what's going on here. That's how we need to phrase it to be nice and proper. As the delta x gets close to 0, as the delta x approaches 0, our slope is approaching 1/3. Now, we've just looked at this from a little bit above. We might also want to look at this from a little bit below. So we might want to look at things like 2.9. So from the other side, we can check what happens as we approach 0 from the other side. And it certainly looks like the same thing is happening. As I get a factor of 10 closer, we throw another 3 in there. So it looks like from the other side, we are also approaching a 1/3. So we should consider this from both sides. But this is the idea. As delta x gets close to 0, the slope is getting closer to 1/3. How's everybody okay? At this point, we've got a very hand-wavy idea about what's going on. We wave our hands and build intuition. So, well, as the delta x gets closer to 0, the slope gets closer to 1/3. Closer to 1/3. That's why we call it hand waving. When a mathematician waves their hands at things, they don't want to explain things to you. So I do the explanation with my hands all nice and still. And you're like, well, I'm not really sure about that. I do exactly the same explanation, but I start waving my hands. And then somehow that helps. But really what happens is the student recognizes, you just said the same thing, you just wave your hands. So like, oh, I don't want to see where this goes. So, okay, I got it now. And then people clap. And you're like, oh, yes. Well, you didn't. You just waved your hands. I mean, I wish I could do that. I wish I could just Jedi mind trick. You all understand calculus now. I have a feeling you would understand calculus the same way ChatGPT understands calculus, that you don't. You just like imitate. So from a Jedi mind trick standpoint, I have to be like, oh, you're all going to go home and study calculus. And then you're not going to show up the next day. I'm like, oh man, that went badly. Because you're all sitting there thinking, no, I have to study calculus because of the mind control. And I go, oh dang, now I have to go individually to your houses and say, you can stop studying calculus now. But then you never come back. It's a real big mess. That's why I'm not allowed to use mind control anymore. What we really want is the matrix version of things. We just come in and sit down and say, oh, hi, welcome to Calc 1. Everybody go ahead and plug your brains in. I really hope that we didn't put it back here. That'd be super inconvenient. Let's do a cyberpunk thing where you can just like plug it into your wrist. And like, oh yeah, plug it in. So you sit down at your desk, plug it in. Actually, you disinfect it first because of COVID, then you plug in. And then I just download Calc 1. And I go, okay, let's begin. Click. Like 3 seconds later, it's like, oh, congratulations, you all have completed your Calc 1 course. If you just exit out that door, go next door, you'll find Calc 2. Good semester, everybody. And it'd be like 5 minutes, a whole university. You know what I mean? Matrix style. Why can't we have that part from the Matrix? Why do we have to live in this Matrix where it requires work? It's just like arbitrarily we decide individually, each person needs a different amount of time. So fucked up. You can all just have it instantly. Here's the idea that we're the thing that we need. This is what we're headed towards. Right now, our explanation is way too hand-wavy. As delta x approaches 0, the slope is approaching 1/3. What do we mean by as delta x approaches 0, the slope approaches 1/3? What do we mean? What do we mean when we say this? As delta x approaches 0, the slope approaches 1/3. Let's write down what we mean. Here's an abbreviation because this is a math class and we have abbreviations for everything. Everything abrev. This says the limit as x approaches c of f of x equals L. That's why we wanted to write the symbols, if it's shorter. But this part here says the limit as x approaches c of f of x is L. Then we're gonna define what that means. The limit as x approaches c of f of x is L if and only if, that's what mathematicians say when we're defining something. If and only if is if A, then B, and if B, then A. These two things are equivalent. And we abbreviate that shit too. If and only if limit as x approaches c of f of x equals L if and only if for every epsilon greater than 0. So that's how I write a lowercase epsilon. I make a backwards 3. This symbol looks like a D that got hit from the side, and like the vertical part of the D got dented. So it got hit by a truck or something like that. Kind of like make it go this way and then come back up. That's a lowercase delta. Specifically, it's my attempt at a lowercase delta. The limit as x approaches c of f of x equals L if and only if for every positive epsilon, there is a positive delta such that the absolute value of x minus c less than delta implies that f of x minus the absolute value of f of x minus L is less than epsilon. So this arrow is implies absolute x minus c less than delta. This says x is within delta units of c. This arrow is implies. And f of x minus L less than epsilon in absolute value means f of x is within epsilon units of L. We can say that the limit as x approaches c of f of x is equal to L if whenever we're close enough to c, x is close enough to c, f of x will be close to L. How close? As close as we want. Epsilon is our chosen tolerance. Epsilon is how close we want to be to L. If we can find a delta for any choice of epsilon, then we can say that the limit as x approaches c of f of x is L. Step 1, we'll write this down along with the notations so that you could read it proper without just spelling stuff. Step 2, we're going to draw a picture of it and think about it some more. Step 3 is we're going to think about it some more. Step 4 is we're going to think about it some more. Step 5 is we're going to think about it some more. And at some point along that way, you're going to say, is this going to show up on a test? I'm being like, oh no, then we're going to stop thinking about it immediately. But it doesn't matter because I'm going to have you think about it so much, you're stuck with it now. It's a song stuck in your head. I don't know what the current song stuck in your head is going to be for today. I have not turned on Spotify in quite some time, so I can't pick one. Any questions? I'm also unwilling to pull out my phone and see what's on Spotify right now, because who knows what it might be. All right, that's going to do it for today. Think about the hand-wavy ideas that we had, the intuition, and this is how we're going to make it rigorous. This is the point of math. That's it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.